We are now going to complete the environmental model looking at the context diagram, the preliminary data dictionary, and the requirements list. The context diagram graphically depicts the system boundaries, highlights the outside entities the system must communicate with, depicts the data at a very high level received from and sent to the outside entities. The context diagram really is a summary picture of the external event list. There is exactly one process on the context diagram representing the entire system being modeled. Data flows exist between external source sinks and the system process. There cannot be any data flows between source sinks. Use this fact to help determine who or what is inside or outside the system. As you'll see, the picture that the context diagram shows is a bit enhanced, as it shows the flow of information out to external entities, which, as we mentioned in learning about the external event list, will often occur at some later time after information has arrived to flow into the system. It's a question to be asked: do we need to track communication between source sinks? So here is our example from the CGFNS model. Please note that the names associated with the information or data flows are very general in nature, which is typical for context diagrams. This reflects the fact that each such flow is an aggregate of multiple flows that will go to different parts inside the system when we later model a greater level of detail. You can enter the statement of purpose, or perhaps the external event list, in the Visible Analyst repository as the definition or description of the context diagram process 0. And we'll demonstrate that later with the solution for the exercise when you draw your context diagram for the Get a Grip Incorporated case study. So as you see here on the diagram, we show the one process bubble for the system for CGFNS and all of the source sinks that we talked about and saw in the external event list. The final element of the environmental model is the data dictionary. As previously mentioned, the data dictionary is implemented as a repository in a case tool such as Visible Analyst. The data dictionary shows definitions of the context diagram's data flows and the ERD's entities and relationships, essential to ensure validity of captured requirements because we here have details that are really at the nitty-gritty level, which often receives short shrift, but provides significant long-term benefit in contributing to a successful project. One additional item that you can note in the repository is the owner by analyst, which is different than who in the business owns a particular piece of information. So here is an example from the data dictionary. And as you can see in a repository, more than just the definition of each model element is captured. In particular, if you note the item here, applicant demographics, we'll see on the next slide that that is a summary level piece of information, what we call a data structure. And we can hide additional detail behind this intermediate level. So a repository allows you to build intermediate constructs that help hide complexity and make it easier to grasp and document system requirements. And again here, even in the applicant demographics, is another data store, this time applicant address. And as we see on the next slide, that the address has substructure, this time individual data elements. There is no actual limit to how deep substructures can go, but there is a practical limit, and that limit is pretty close to what you see here. At this point, we would look at an individual data element and its physical characteristics that describe exactly how it is to be stored. It is at the atomic level of data at this point. The last thing I want to talk about before we move beyond the environmental model isn't strictly speaking a part of the requirements model at all, but rather a bit of a throwback to requirements definition without structured methods, but substantially repurposed. And that is that the requirements list is used as a narrative list of the new system's functional requirements. Primarily, its purpose is as a starting point and reference during the course of meetings and reviews of the models being developed. It's something that can be used to capture offline items identified, for instance, during a JAD session, and information that does not have an obvious home elsewhere in the model at the time of identification. You should note in the repository as each requirement is accounted for in the model and which requirement each process specification is implementing. You can document requirements in the repository using the planning statement system requirement repository entry type. You can also create a user-defined object requirements list, which would be a composite type and contain a set or subset of requirements. The main difference between our use of the requirements list and a non-structured approach use is that we have no need for the list to be complete, only that anything that ends up on the list that is to be included in the final product is accounted for in our models. So here, again, we have some examples from CGFNS. For a somewhat lengthy example, what you will note if you take a peek back at this list when referring to the CGFNS requirements model is that some of the items on the list are not included and were not implemented in the system that was built, as they were, in the end, out of scope. This implies another difference in how we can employ this list as a place to put something that is unlikely to be implemented, but is put forward by a business user whose input is needed, if not in this particular instance, and needs to see their input put someplace. So basically, that you don't turn them off by ignoring something, even if it may not be something really relevant. We have a place to put it, and everyone is happy. So again, here are the examples. For instance, to put credentialing resource material online and allow inquiry in various ways, this is a requirement that was beyond the scope of the system and did not get implemented. But to maintain the status of the applicant file, that was extremely important and did get implemented, and we were able to note in the Visible Analyst repository the specific process where this requirement was met. Here are additional requirements, such as registration date versus deadline checking, and applicant search capabilities. We'll talk a lot about this later on. This was a very important requirement. Generating communications to the applicant regarding application status. You've already seen some things about this in the event list for CGFNS, where, and also on the state transition diagram example, where additional information or materials were required from the applicant, and they had to make sure they let them know. Again, additional items here: maintain historical records of communications, exam center information, administration processes and procedures. That was something that didn't make it into the final product. So again, we have quite a number of things that did get captured on their requirements list. Some were kept and documented and implemented, and others were not. So, at this point, we've really finished reviewing the components that make up an initial pass on modeling the system's requirements. And now we're going to circle back to do a more complete job. So, we're going to look at completing the requirements model. To accomplish this, we will use pretty much the same constructs as for the environmental model, with an extra item or two to wit. So, the completing the requirements model will again involve creating the complete model with a detailed elaboration of the preliminary depiction of the requirements that were put in the environmental model. Again, the modeling tools and structures used are entity relationship diagram, entity lifecycle state transition diagram, data flow diagram, data dictionary, and a new item, the process mini specification. Now, I had suggested keeping a copy of the slide with the relationship of the system models handy. Now is a good time to refer to it and get a sense for where we are. The context diagram is a data flow diagram. The entity relationship diagram we've seen before. Now we're going to delve into this and into its constituent parts in greater detail. And again, the entity relationship diagram shows the relationships that exist among the stored data of a system. Describes also the stored data layout of a system at a high level of abstraction, one of the things that you'll see repeated in all of our modeling constructs. So, the entity relationship diagram consists specifically of fundamental entities. An example would be a desk, a representation to define a fundamental entity of a set of real-world things such that all instances of the set have the same characteristics, and all instances are subject to and conform to the same rules. The second element of an entity relationship diagram is the relationship. The relationship is an abstraction of a set of associations that hold systematically between different kinds of things in the real world. For example, the desk is accompanied by a chair, and a chair accompanies a desk. Note that we talk about relationships from both directions when discussing how two entities are related. I also want to point out the numeric aspect, the cardinality as we call it, and the crow's feet notation you see here very nicely depicts exactly how that should be read, where the two lines next to each other indicates 1 to 1, that there's a mandatory relationship. Next, on the other side, the 0 to m, the 0 to many relationship, and again, the 1 to 1 and the 1 to many. The 0 to 1, this is an optional relation on that side against the 0 to many, and the optional relation on one side and the mandatory on the many side. The next component on an entity relationship diagram is the associative entity, also known as the junction entity, or a correlation table. This representation represents a relationship that has information associated with each instance of the relationship. So an example of that would be an employee equipment list that would relate employees to items of equipment. The next type of entity is an attributive entity. An entity of this kind refers to and further defines the characteristics of a fundamental entity. An example of that would be an invoice line item, or anyway, a table that would contain such things, because they further define the header of the invoice. The next element is the attribute, also known as a data element. This is the abstraction of a single characteristic possessed by all the real-world things that were abstracted as an entity. So, for example, the attributes for a fundamental entity of a desk would be the height, the length, and the width of the desk. All entities can and most often will end up being implemented as tables in a relational database with attributes implemented as data elements or fields in those tables. Now, since we know what the pieces of an ERD, an entity relationship diagram, are that are used to create one, we need a series of steps we can take to make use of them to represent real-world information. We'll swing back around to get into the details of what normalized data is and how to do it shortly. But first, let's just start with the heuristics, as we call it, the steps we can take to create an ERD. So the first one is to identify candidate entities as nouns in the external event list. We name these as a singular noun phrase. We identify as many potential attributes, data elements, as possible from existing forms or reports or screens or anything else that might be present that we can use to identify them. We will then normalize these attributes, and again, we will talk about that in detail shortly, through what we call third normal form. We will assign normalized sets of attributes, data elements, to entities in the ERD. Then we will identify and document relationships between entities. Name each of these as a verb phrase. We will add subtypes, if there are any, beneath an entity if some attributes cannot apply to all instances of the entity type. We will create a supertype above entities that have attributes that are in common. So an example of a supertype would be vehicle for subtypes of entities such as a passenger vehicle, who would have the number of passengers as a different type of data element, or a truck, which might have cargo capacity as a unique element, or a train that might have the gauge of the rail it runs on as a different data element.